Hello students, Intermediate Maths, Paper 1A, Chapter number 1, Functions, Ordered pair. Let A and B be two sets. If small a belongs to capital A, small b belongs to capital B, then A comma B is called an ordered pair. Is an ordered pair. And this is called the first component. Second one is called second component. Or first coordinate, second coordinate. Second one, Cartesian product. So the set of ordered pairs is called a Cartesian product. It is denoted by A cross B. For example, set A has the elements 1, 2, 3. Set B has x comma y, two elements. Then it's a Cartesian product. So Cartesian product of A and B is denoted with A cross B. The Cartesian product is 1x ordered pairs, set of all ordered pairs. 1 comma x, 1 comma y, 2a comma x, 2 comma y, 3 comma x, 3 comma y. So this is the cross product A cross B. So A cross B, which is not equal to B cross A. Because in B cross A, the ordered pairs are x comma 1, x comma 2, x comma 3, y comma 1, y comma 2, y comma 3. So those two are not equal. Next one is a relation. Any subset of A cross B is called a relation from A to B. Relation from A to A is called a binary relation. So A cross A is a binary relation. Number of elements in the above example A cross B equal to A is 6, 1, 2, 3, 4, 5, 6. Number of ordered pairs in A cross B is 6. So number of subsets. So total number of subsets. The formula is 2 power n. So 2 power, this is n, 2 power 6. So 2 power 6 is 64. So totally there are 64 relations we can form from the above example. So number of relations in this example is 2 power 664. So we can define totally 64 relations. Okay, next fourth one, function. Take two sets, two non-empty sets, A and B, be two non-empty sets, and F be a relation from A to B, then if for each A belongs to A, each element A belongs to A, there exists a unique element B belongs to B such that A comma B belongs to F. Then F maps A to B is a function. Here this is called, the first set is called the domain, and this is the second one, codomain. Next one is inverse function. If a relation R is from set A to set B, then inverse of relation R is R inverse, which is equal to y comma x, ordered pair y comma x for all x comma y belongs to R. Okay, suppose R maps A to B, then its inverse function is set B to A. Okay, for example, R is 2 comma 4 and 3 comma 5, and its R inverse function is 4 comma 2 comma 4, here it is 4 comma 2, and 3 comma 5 in R inverse it is 5 comma 3. Next one, 1 function or an injection. So if different or distinct elements of A have distinct F images, distinct images in B, or can also define it as a function F is 1 1, if and only if take two elements A1 A2 in the first set and f of A1 equal to f of A2, then A1 equal to A2. Okay, f is 1 1, there are two definitions, A1 A2 two elements in A, and f of A1 equal to f of A2, then A1 equal to A2. An example for this 1 1 function, take two sets okay. In set A we are taking three elements A, B, C. In the set B we are taking elements 1 2 3. So A is mapping to 1, B is mapping to 3, and C is to 2. So A comma 1, B comma 3, C comma 2. Yes, this is 1 1 function. Yes, it is 1 1. Okay, take another example. In set A we are taking again A, B, C, three elements. In set B we are taking only two elements. A is mapping to 2, B is also mapping to 2, and C is mapping to 3. So this is not a 1 1 function. So not 1 1 function, because different elements in first set has different images in B, but here A is mapping to 2 and B is also mapping to 2. So here the image is same for these two elements. So this is not a 1 1 function. Okay, if F maps A to B is a function, then take an element A and it is B. Okay, we can read it as f of A equal to B. Okay, then we can read A is mapped to 1. A is mapped to 1. And in another way we can read it as B is image of A. And we can also read it as A is pre-image of B. A is pre-image of B, small b. Okay, A is mapped to B. A is mapped to B. B is image of A, and A is pre-image of B. Take an example. F maps R to R defined by f of x equal to 2x plus 1. Then let take two elements A1, A2 belongs to the first set capital R. A1, A2, two elements in the first set. Okay, and also take f of a1 equal to f of a2. Okay, f of x is defined as 2x plus 1. Then f of a1 is 2a1 plus 1. So 2a1 plus 1 equal to 2a2 plus 1. Both sides cancel 1. So 2a1 equal to 2a2. Both sides cancel 2. Then a1 equal to a2. So then by the definition it is 1 1. Therefore f is 1 1. Is 1 1. Now take another example. If maps R to R is defined by f of x equal to x square. So again take two elements a1 a2 belongs to first set, and also take f of a1 equal to f of a2, and f of x is defined as x square. F of a1 is a1 square equal to a2 square. Okay, then you can write it as a1 equal to plus or minus a2. Okay, here for a1 there are two images. For the first element there are two images. So a1 a2 plus or minus a2 plus a2 minus a2. So this type of function is not 1 1 function. Therefore f maps R to R is not 1 1. It is not a 1 1 function. Okay, or we can take the example like f of x equal to x square. So x square f maps R to R. R is real number system. So take any one number f of 1. So for f of 1 it is 1 square 1 only. But f of minus 1 whole square equal to 1. So for minus 1 and plus 1 the image is same. So it is not 1 1. Is not 1 1. Hello students. Next one is onto function or surjection. If the range of f is equal to the codomain of f. F maps A to B is a surjection if and only if the range of f equal to B, second set, or B equal to f of A where A belongs to A. You can also define it as range equal to codomain, or for every second set, take any element from the second set, for every B belongs to B there exists at least one element A belongs to capital A, such that f of A equal to B. So these are the definitions for onto. So every element in B has a pre-image in A. Take an example. Take two sets A and B. In first set we are taking 4 elements 1 2 3 4. In the second set we are taking only 3 elements A B C. So one is mapped to A, 2 to B, and 3 maps to C, and 4 is also to C. Okay, here F is onto, but F is not 1 1. The reason is range equal to codomain. every element in second set B has a pre-image. So each and every element is mapped with the first set. Range equal to codomain. So this is onto. F is onto. Okay, but what is about F is not 1 1. So F is 1 1 means for different elements in A have different images in B. But for 3 the image is C. For 4 also the element 4 has the same element C. So F is onto, but in case of 1 1 it is not 1 1 because F of 3 equal to F of 4 equal to C. For 3 and 4 the same answer, same image. So this is not 1 1 since same image. Take another example. Take two sets A and B. You take the same 1 2 3 4 A B C, 1 to B and 2 is also mapped to B, 3 to C and 4 is also mapped to C. Here is it 1 1 or onto? Okay, just check it. F is not onto because what is the reason? There is no pre-image for the element A. There is no, since the reason is there is no pre-image for the element A. And F is not 1 1. Okay, the reason is for F of 1 and for F of 2 the image is same. For F of 3 and F of 4 has the same image as C. So it is not 1 1. So this function is not 1 1 and not onto. Okay, now bisection. So if the function F is both 1 1 and onto, so then that is a bisection. That function is a bisection. Next one, equality of functions. Take any two functions f and g. If domain of f equal to domain of g, then those two functions are equal. Next one, constant function. The range of f contains one and only one element, that is f of x equal to c. For example, in the first set take 4 elements A, B, C, D. In the second set take only one element 2. If A is mapped to 2, B is also 2, C, D. So here f of A equal to f of B equal to f of C equal to f of D. All elements the image is the same. So this type of function is called a constant function. Next one is identity function. Let A be a non-empty set. F maps A to A is called a identity function on A. It is denoted by IA. So take an example. If A equal to 2 elements in a set, A has 2 elements. Okay, the same sets we have to take here, A to A, so AB, here also AB. So this type of function is an identity function. Next one, composite function. If two functions F maps A to B and G maps B to C, then the relation A comma G of F of A, G of F of A, such that A belongs to A is called a composite function of g. With the EF it is denoted by G circle EF. Take three functions, three sets A, B, C. F maps A to B, G maps B to C, then G circle F. G circle F maps A to C. So G circle F maps A to C. This is a composite function. Real valued function if X is any set, F maps X to R, then F is called a real valued function. For example, f of x by g of x, g of x not equal to 0, take log x, here x must be positive greater than 0, and take a root of f of x, under root non-negative number, negative number does not exist, so f of x must be a positive number, it may be 0 also, 1 by under root f of x. So here f of x must be just greater than 0. So these are the examples for real valued functions. Next one, even and odd function. If f of minus x equal to f of x for all x belongs to A, then here f maps A to R. F of minus x equal to f of x, then f is called an even function. Okay, if f of minus x equal to minus f of x, then it is an odd function. For example, take f of x equal to x square, f of x equal to cos x, f of x equal to mod x. So for all these are all the functions are even functions. So examples for even functions. Because if you take any negative number, it will be positive again. So you will get again f of x. So that's why it is an even function. Next, for odd function, some examples are f of x equal to x. It is an odd function. Next example, f of x equal to x square plus x cube. Then this is neither even nor odd. Next one is polynomial function. The function f is defined on R by f of x equal to a0 plus a1x plus a2x square and so on an x power n for all x belongs to R, where n is a non-negative integer and a0, a1, a2 so on an are real numbers. Rational function. If f and g are polynomial functions and g of x not equal to 0 for all x belongs to R, then f by g defined as f by g of x equal to f of x by g of x. This is called a rational function. Next, 17th one, algebraic function. a function obtained by applying a finite number of algebraic operations on polynomial. It is called an algebraic function. Next, 18th one, exponential function. The function a power x, where a not equal to 1 and which is greater than 0 and x is rational. This type of function a power x, it is an exponential function and its domain is R and its range is R plus. Take an example of exponential function. For a equal to 1, the graph looks like this. Another example, y equal to 2 power x. For x values 0, 1, 2, put x equal to 0, then 2 power 0 is 1, and if you put x equal to 1, y is 2 and it is 4. The graph is, so for a greater than 1, here it is a equal to 2 which is greater than 1. So for a greater than 1, the graph looks like this. The same way, for 0 less than a less than 1, for a equal to 1, the graph is like this. For a is greater than 1, the graph is an increasing graph, and if a is less than 1, the graph will be like this. So if x increases, then there is an increase in y. Next one is a logarithmic function. If a greater than 0 and which is not equal to 1, given y is also greater than 0, then there is an unique x belongs to R such that a power x equal to y. So this type of function is a logarithmic function. The function is defined on R plus. Okay, suppose a power x equal to y, you can also write x equal to log y base a. Base a. If the base is e, then that logarithmic function is called a natural logarithmic function, and it is denoted the natural logarithmic function. So in this natural logarithmic function, e power x equal to y, then you can write it as x equal to log y base e. And its domain is 0, infinity and range is R. Next one is greatest integer function. The function if maps R to R and defined by f of x equal to step x. This is called step x for all x belongs to R. It is called a greatest integer function. Okay, and its domain is R and range is Z. In the graph of greatest integer function will be like this. Okay, the greatest integer less than or equal to x. Like suppose take an example 1.5. Okay, take an integer because the range is always an integer. So for 1.5, 1. For minus 2.5, it is minus 3 because minus 3 is less than minus 2.5. Next one is modulus function. the function f maps R2 are defined by f of x equal to mod x for each x belongs to R. F of x, it is positive x for x greater than or equal to 0, and it is minus x if x less than 0. The graph of y equal to mod x is, because all are positive values. This is the graph for y equal to mod x. Okay, next one is signum function or signum function. A function f from R to R defined by signum of x equal to f of x, which is equal to mod x by x. It can be defined as, if it is positive x is greater than 0, the answer is 1. For x equal to 0, signum function is 0. For x less than 0, it is minus 1. So its domain is R and its range is